Hello everyone, and welcome back to another Geostats lecture video. And in this lecture video, I want to talk about the p-value. Or more importantly, what we can test, what sort of p-value tests we can run given our local Morans eyes. We're going to talk about an issue called multiple hypothesis testing in a later video, so we're not going to worry about that right now. But basically what I want to do is I want to talk about two different hypothesis tests, right? Maybe p-value wasn't the right word. Let's erase that for a second. We're going to talk about two different hypothesis tests. For local Morans eye, right? And so there's two different ones, right? Up to this point, all of the other test statistics we did, we had sort of one that we ran the p-value for. We had one hypothesis, and it was whether or not this was statistically significant. But for local Morans eye, we actually have two that we are testing for. And so the first here is going to be, so test one is a test for normality. Right. So the test for normality is going to sort of make the assumption that the values of our local Morans eye follow a normal distribution, which would indicate that the vast majority of our local Morans eye values should have values close to the mean, right? That's kind of what it means to be normally distributed. So we're going to test that assumption. We're going to say, okay, well, are our local Morans eye values normally distributed? All right, so our null hypothesis, is going to be that the local Morans eye values are normally distributed. Right? That's what we're sort of hoping to reject. So you might be saying, well, why would we want to reject this, right? Most of the time when we test for normality, normality is a good thing. Well, you have to remember, right? The idea here is that the extreme positives and the extreme negatives are the values that really indicate whether or not we have these pockets of autocorrelation happening. So we would actually want our data, or I shouldn't say we would want our data, but rejecting this is an indicator that we have these statistically significant hotspots occurring. Right? It's saying that, hey, this value is coming from a not normally distributed population, meaning it's an extreme value. Okay. So our alternative hypothesis is that the local Morans eye value is not from a normally distributed population. Right, meaning this is truly an extreme value. Right, that's what this is saying, is that, hey, this value is actually an extreme value. So that's what it means if we can reject the null hypothesis. Now, I want to make something clear here. When we're doing these hypothesis tests, we're getting a p-value for each individual polygon, right? Just like before, every other time we've done this, right, we had a test statistic and a p-value. But if you think about these LISAs, right, we're getting a test statistic for each polygon. And this will make a lot more sense when you go through the R examples, right? So each polygon has a test statistic. So each polygon has a p-value. And that p-value is basically saying, hey, does this I value come from a normally distributed population? And if it doesn't, right, that's an indication that it is actually a significant extreme, either high or low. All right, so let's look at test 2. So this is the test for randomization. Right, and this is the one that we most use. Right, this is the one that is sort of used by default in the SPDEP package that we use to calculate these things. So the null hypothesis for the test for randomization is that there is no spatial autocorrelation, right? There is no spatial association, right? Basically what this is saying is that, or I guess the best way to explain this is that we're saying that the location of the values doesn't matter, right? So what we're saying, they say the word permutation, right? Basically, we're assuming that any permutation of zi's are equally likely, meaning that my location could have the zi value of any other zi in the data set, and it wouldn't change the local I. Right. So this is the one that we use most often. And then is that there is spatial association. Right? That there is spatial association, which is basically saying that, hey, this value that we have is not only an extreme value, but it's also the location matters, right? I cannot have a different z value. My z value matters to me, and there is an association, a spatial association with that. So hopefully this makes sense. I know it's a little confusing because we have the two different tests. Just keep in mind here that the test for randomization is the one that you're most often going to use, because this is the one that is specifically testing whether or not my zi value matters to me relative to I could have the zi value of any other polygon in the data set, and then it wouldn't really matter. Hopefully that makes sense. I know that's a little confusing. But if you have any questions, I encourage you to please pause the video, go back, rewatch the parts you're confused about, and as always, please reach out. Thank you.